Hello everyone, welcome to my channel. Now let me talk about supplementary two functions of two random variables. The problem is, suppose we have two random variables, x and y. And right now we want to define two functions, g and h. And through the two functions, we have the mapping from x, y to z and w. And right now we want to know how to determine the joint PDF FZW of z and w. So how to do? Actually, we can use the similar procedure. So that's why you see we have the procedure same as the previous chapter. If we have a single random variable from two variables that says x, y to z, for example, in the past. But right now we have the procedure for two random variables rather than a single random variable. But still similar to the previous one, so we need to start from CDF. So join CDF here. Alright, so Z and W. So in terms of a function G and H. And likewise, if we have the inequality, then we can form the region. And this region says, oh, we can accumulate the probability based on the region. And now we have two variables, x and y, so of course we should find the region on the plane of x and y. Because of two dimensions, so we have the plane x and y, and within the region D, ZW to have the corresponding region. Through the double integral, then we can find the probability for CDF. So similar to the previous one, right now we still have the similar one to find the region. Well, if we can use CDF first and then we can find the PDF. But right now it's join CDF and then we have the join PDF. Once we have the join PDF, actually we can have the marginal PDF. So later we can show you how to do. To have the derivation, we can consider this example. Example 9.1. And 9.1, we have the variable z and w, minimum of x and y and maximum of x and y, and set minimum to z and set maximum to w. And we are asked to determine the joint PDF z and w. Well, if we have this, actually we assume we have the independent, uniformly distributed random variables within the interval z to theta. For this one, to have the joint CDF, we need to have the derivation. Of course, how about z lower than 0, w lower than 0? Actually, we know, oh, no probability, so of course, 0. And we need to consider the following two cases. Case 1, z larger than or equal to z. Case 2, z smaller than z. This is case 1. And this is case 2. For case 1, we have W larger and case 2, W smaller. Alright, so for the two cases, then we can consider this. Case 1. Alright, from case 1 and the corresponding figure, this figure. Then what's the region? The region should be this. So we want to know why the region should be this. Right? So why this region? Look at this. It says we have a z. Sorry. We have a minima. X, Y. This is the minima z, lower than specified z. And maxima, X and Y, lower than W. Alright, so we can have the situation. If we have the region here, look at this. Alright, so this is W. So W actually maxima. And this is, so here, sorry. So W here and W here. And another one. It's a Z here. Alright, so it says if we have a Z lower than Z and maxima lower than W. So you can look at this. The region here, why it should be this? We have minima, so assume we have x large. So for example, x larger and y smaller. So for this case, then this one minima, so it's x lower than z. And this one, y lower than w. Alright, so x larger and y smaller. So here, look at this one, x larger. Alright, and x larger, then we have this interval, x smaller than z. And y lower than w. So we have this. And likewise, how about this if x smaller and y larger? So this one, it should be minimum. So let me change maybe something. X larger, so this one should be y. Sorry, let me have the correction. And this one, it should be x. So let me have the correction here. So it says x larger, so x larger and y smaller. It should be this. So y lower than z, this one. Y lower than z. And x lower than w here. So actually this one. Sorry, let me have the correction. Otherwise, if x smaller, so x lower than z. And this one, y lower than w. So y lower than w, x lower than z, so this one. So that's why we have the region here. Alright, so first of all, we can look at this from that figure. So we have the area. If we have the area, how to have the probability, CDF. Alright, so CDF ZW, the probability actually follow the region. So we have this. And how to have the probability? The probability can have this. This probability x is equal to z, y lower than w. So zw actually is this. And another one is y equal to w, x equal to z. But we have the overlap region. Here, this one, z and z, overlap region. We need to minus the overlap region. Alright, so we have a CDF for this case. And how about if we have a case, second case? W lower than z. So let me erase O. Second case. And again, right now, assume y large and y smaller. So we have this. Y lower than z and x smaller than w. Alright, so if so, smaller than w here because of w smaller than and y lower than z here. However, y small, so of course should lower than this as well. Alright, so we have this already. And likewise, we have x small, but y large. So we have y large here. Alright, so we have this. The largest one lower than w. So of course this one should lower than w as well. So actually OW. So that's why for this case we have the region. If we have the region, then we can find CDF. CDF only this one. OW to find the probability. If we have the second case, case 2. Well, this is the two cases to have the joint CDF. And right now we want to have the derivation. So we have the joint CDF of x and y because of independence. And uniform, so it's the product form. Therefore, we have the formula for the joint PDF. Joint CDF. If so, then we can pass on the formula here. And substitute the formula to the first one, second one. For example, second one is true. We have OW, so we have W squared over sigma squared. And for this, actually, x and y, it should be ZW over sigma squared. And plus the second one, ZW over sigma squared. And minus ZZ, so Z squared and sigma squared. So we have 2 ZW and Z squared. So this is the formula here. Alright, so if we have this formula, finally we have PDF. PDF actually should have the partial differentiation with respect to Z and W respectively. Oh, how about Z first? Actually, this one can be constant. So finally it's 0. And for this one, Z first. So Z first we have this W and 2Z. And the W later, this one vanish. So we have 2. So we have 2 over sigma squared. So this is the joint PDF. Once we have the joint PDF, and then we can pass on this to have for the next one. But before we have the next one, look at this. We have the corresponding region. Because of a uniform, so lower than theta. But this is the first case, and this is the second case. Alright, so only the first case, so care about the region. Care about that region if we want to find marginal PDF Z, so we have a W. And W, what is the region for W? W here. Oh, okay, W, we have a Z to theta. So Z to theta. As for the remaining, you can follow the integral, so we have this result. So this is the marginal PDF. And likewise for W, W actually over Z. Z actually the range here. Z. So Z actually 0 and W. 0 and W. So finally through the integral, we have the result. So we have the marginal PDF. Okay, so this is the way based on join CDF first and then join PDF. After join PDF, then we can find the marginal PDF. This example illustrates the procedure to do this. And in the following, similar to the previous one, we want to have a formula. So is it possible to have a formula? It says yes, it's possible to develop a formula to obtain the joint PDF directly. So later we have the formula, and now you know the reason why we have the formula. So actually, if we have a given point ZW, and then we can have the corresponding point. Actually, we can have many. So for example, 1, 2 to n. Here, we can have Z and W here. We can have a mapping 1, 2, 3 to n. Alright, so 1, 2 to n. Actually, if we have a given one, we can find multiple cases possibly. So we assume we have n points. And later we will use the relationship to derive the relationship for this one to this one and the other one, but finally we will choose one to serve as an example. And if we want to find the corresponding joint probability density function, then we need to consider the problem of evaluating the probability. Z within the interval and W within the interval. And actually this one should be equal to multiple points within X. But first of all, we check Z only. For Z only, actually we can pass on that one, Z and W, and multiply the area. Alright, delta Z and delta W. Someone like, oh, okay, O can be approximate here. And we find the area. And use the area to multiply the corresponding probability. Then we can form the probability. Alright, so we use approximation. So here it is the approximation. Even approximation, later we can have the corresponding integral, then we can have the probability. But right now, we can have the corresponding region described by multiple. For example, 1. And here we have I in general. So we have the corresponding mapping A to A prime, B to B prime, C to C prime, and D to D prime. Well, then we can have the further discussion. We can translate the probability in terms of X and Y. And we need to have the probability for this region. And how to have the probability for this region? So later we want to find the probability for this region. Well, we will have the corresponding parallelism. Alright, and the parallelism with the area delta I if we consider the ith point. And if we consider that probability, actually we can consider, oh, okay, we have the area delta I. If we have the delta I, actually can be approximated by delta I multiply the corresponding probability, joint probability density function, and sum of all the probabilities. So that's why we have a summation. And so previously we have this one, delta Z, delta W here, probability equal to this way, and move delta Z and delta W to the denominator. And so that we have the formula, this formula. To calculate delta Z, delta W, fine, no problem. But we have the further task to evaluate the area of delta I of the parallelism. Well, maybe you have a question. Why rectangle and the parallelism? Same, it's here exact. But this one, something like can be approximate. But approximate, if we can have an integral, this approximation is feasible. So that's why we use the parallelism to have the area calculation. If we have the area calculation based on the parallelism, and then we can show how to have the result. Again, we have the mapping. Okay, for example, it's I. Alright, so here it can be I or maybe it's 1. It doesn't matter. So we have the corresponding point. Say it's I. Alright, so if we have the corresponding one, we have the point A prime here, xi, yi. And how about the point B prime? B prime, actually, we should find this. It's delta xi. If we move this to the left-hand side, and this is delta yi if we move this to the left-hand side again. And right now we have this z. We have delta z. Alright, if so, this one, delta xi, how to have the results? Because we have the change delta z. So only delta z. And delta z, how to have for the corresponding? This one, delta z. So how to have the corresponding changes in delta xi and the delta yi. So here it's delta xi. It should be, okay, so we have the slope for x. Look at this. Here, delta xi. Only the changes in delta z. So we have the differentiation. And here we have slope. Here, this is slope, and multiply the increment. So that's why we have the first one, perform partial derivative with respect to z. Partial derivative with respect to z for function h1, but multiply the incremental quantity. Alright, so if so, then we have this. However, we can have this. Actually, we can move it to this one. So we have delta xi and delta yi if we just have the increment delta z. And likewise, we can have a c prime, but increment of delta w and delta w. Same for function 1, function 2. Well, if so, then we have the corresponding coordinate for C prime and B prime. In fact, we have delta xi and delta xi again. If we remove this delta xi, delta yi, if we have the increment on z and w plane, on z and w plane. Well, if so, how to have the area? Area actually we just consider delta xi and delta yi. So what it looks like, this one. Here we have delta xi and delta yi. Something like delta xi 0, 0 and delta xi. But right now not delta xi, so delta xi. And we have the corresponding angle phi and corresponding angle theta. If we have the given one, look at this. How to have the probability? Right now, A prime, B prime, this one should be delta xi here. And A prime, C prime, it should be delta yi here. Alright, so delta xi, delta y are actually the length of A prime, C, B prime, A prime, C prime. Well, so how to have the area? Oh, length of A prime, B prime, and A prime, C prime, multiply the angle. And if we have a triangle, it should be a half. But this one is the parallelism, so multiply 2. So that says we can cancel 2. And cancel 2, then we have a unit 1. And about the formula here, sine theta minus phi is equal to cosine theta sine phi minus sine theta cosine phi. So this one, A prime B prime with the angle phi. So that says A prime C prime, sorry, A prime B prime with the angle phi. So we have sorry, this one wrong. Sine cosine. Let me have the correction. So cosine phi first, and then A prime C prime we have a sine theta. So check it. We need to change. So this is cosine. The formula should be this. Sorry, let me have the correction. So cosine theta, A prime C prime, and A prime sine phi. Alright, for this, actually, previously we didn't have this. A prime, B prime, actually we have for the previous derivation. It should be delta xi, and A prime, C prime, it should be delta yi. And we have the corresponding partial derivative multiply delta z, partial derivative multiply delta w. Alright, so this one actually L prime B prime cosine phi. In fact, it equal to this. This is the delta xi. And previously we have the derivation delta xi. Alright, delta xi related to phi. And this one, delta yi related to phi. Okay, this one. And likewise, delta xi related to theta. Delta xi related to theta. So this one is, sorry, delta yi, delta xi related to theta. So that's why we have h, we have g. So here we use function g1. In fact, it can be gi. Alright, but we follow one. Because of this, we can have the formula. Oh, okay, the formula we have the results. the area equal to this, cosine phi and sine theta. Cosine phi and sine theta. So we have this h1. Sorry, this one. So we have a delta multiply, we have a delta z and delta w moving to outside. So here g1 respect to z and g1, oh sorry. So let me check it again. Here, the area here. So we have the area cosine phi and sine theta. Cosine phi and sine theta. So this one, sorry. So G1 and H1. G1 and H1, partial Z, partial W. And the Z and W moving to outside, and minus this one. Z and W to outside, this one, H1 with respect to Z, and the G1 respect to W. Oh, okay, so this one actually delta I equal to this one. And over this one, then we have this. So we have this term. And this term actually can be shown in a determinant. Determinant here, oh, okay, G1 partial Z and H1 partial W minus this one. So we have a G1 partial W and H1 partial Z. So this is the determinant. And this kind of determinant we can call it Jacobian. Alright, Jacobian, we have the notation Jacobian ZW. And Jacobian ZW actually should be this. Oh, okay, partial with respect to x, y, and, sorry, ZW. Function z and y with partial derivative with respect to ZW. Z and W. Right, so it's x and it's y. Alright, so we have this partial derivative and can be shown in a determinant. And this determinant we call Jacobian. Actually, for the area, it should be positive, so we should have in false, it's positive. Alright. If so, we have a Jacobian and in false positive. So we have this. Oh, the previous equation we can show in terms of this. And likewise, I skip the second one and make it easier. So this one, we have the relationship x, y, perform partial derivative with respect to z and w respectively. So that we have this. Alright, so through the relationship, it's 1, but we need to have a summation. So we have this formula. Alright, this formula. How to have the way to memorize. Look at this. Okay, so we have the probability in terms of ZW. So ZW, we can have delta Z, delta W, all equal to this X and Y in terms of delta X, delta Y. And something like, oh, move it to the outside should be something like, oh, delta X, delta Y, delta Z, delta W. It doesn't mean it's a product directly. I just let you know, oh, okay, we need to know numerator and denominator. And this one actually should be this X, Y, and Z, W respectively. And this is the, sorry, not this one, the previous one, this one. So this is the Jacobian. Oh, okay, even it's not the exact formula, but I just want to let you know, okay, X, Y in the numerator, Z and W in the denominator, and we have the Jacobian. As for why Jacobian, we have the reason, the Y for U. So that's why we have a formula. And how to memorize the formula, previously I already have a way. Alright, so once we have the formula, of course we want to apply. So let's check how to have the usefulness of the formula. So first of all, we consider this example. Example 9.2. We assume we have a zero mean independent Gaussian. Gaussian actually is normal. Alright. And we define a new variable z. It's amplitude. And this is angle. It's phase. Alright, so we have the corresponding region, but we have the amplitude and we have the angle. And of course, first of all, zero mean independent Gaussian or normal, how to have that. And Gaussian should follow the form. This is x, and similarly we have a y square and multiply, so we have the independent joint probability. Alright, so this is a given one. If we have the normal or Gaussian here, so we have the joint PDF. And right now we have z amplitude and w phase. If we have a given point, actually you can pass on the current one. Actually the current one you should know, oh, okay, minus x1 and minus y1, it's a solution as well. So actually we have two solutions if we have the given formula. If I have the given formula, you ever have the polar coordinate to have a z and to have the angle w. So x should be cosine s equal to cosine w, z cosine w, y equal to z sine w here. Because of 2 points, so we have a minus minus. And for both, to determine Jacobian, here it's Jacobian. Oh, the function perform derivative with respect to z and w. So we have this. Z first is cosine. And w and then it's minus sine. And this one, again, it's w, so it's, so wait a moment, this one actually, z and z. Sorry, let me measure this. So here, sorry, x and x, z and w. So x here. So xz, so it's cosine, correct? And w, it's z minus sine. And we have this. And y and zw. Z is sine. And this one is cosine, z cosine. So through the way to have the determinant, it should be z. And we assume z larger than 0. Alright, so actually we have a Jacobian z. And likewise for this, we can have the same one, z. But we have two solutions. Because of two solutions, so OZ, first solution, second solution. For first solution and second solution, each of them have the same one, and we have multiplied 2, 1 and 2. So cancel 2, so that's why we have z. And we have z, so finally we have the results here. Alright, so this is the formula. With the formula, we should notice, oh, okay, the range for z and range for w. These are given, so no problem. But how to have the marginal PDF? This one. Oh, okay, z, then we have a w. W actually, this interval. minus pi over 2, positive pi over 2. So finally, we have this result. And the w actually integral over z here, 0 to infinity. So finally, we have the results. If we have all the results, actually we can have the associate name for the distribution. This distribution actually it can be called Rayleigh random variable, and with the parameter sigma square. And this one is uniform from minus pi over 2 to positive pi over 2. And actually we will have the summarized description, and you can check it. And actually we have the marginal PDF, then we know, oh, okay, it satisfies the protocol, so we can know, okay, Z and W are independent. Okay, so this is the example 2.9.2. And later we will have the next example. So let us continue to apply the formula to this example. Example 9.3. And this time we have U and V rather than Z and W. So solve X and Y, so we have X here and Y here. And partial derivative X to U. Then we have a half. Partial derivative of V, we have a half. And the partial derivative U, it's a half. And another one, negative a half. So we have this. A half, negative a half. So minus we have, so that we have 1 over 2 minus 1. But we have absolute value. Absolute value, then we have a half. And how about the joint PDF in terms of X and Y? Here, we have an exponential, independent. Common parameter, here is a 1 over lambda serving as a common parameter. And then we have a lambda, x over lambda, and minus. And this one larger than 0, larger than 0. And x, y, and multiply, so we have this. And look at this, the interval, we should meet the requirement. Equality, it's okay, so that means include 0. Alright, so we have a given one, and right now a half, so just a half. And because of u serving as x plus y, so finally it's u. And only u, so we have this, only u. And this one, we have the x greater than 0 or equal to 0. And right now, maybe not equal to 0, so we have the requirement. Alright, so this one larger than, x larger than 0. Larger than 0, so finally we have this, u larger than minus v, and u larger than v. So we have u larger than absolute value of v, but lower than infinity. So this is a form. Alright, so this is a requirement. The requirement is important. Once we have the joint PDF, we apply the formula, so we can have the Jacobian multiply the result. Jacobian, it should be partial x, y with respect to z, u and v. So previously we have a half minus f, a half absolute value, so we have a half, simply a half. Alright, so once we have this, you can know, oh, marginal PDF u and marginal PDF v, but u with the region absolute value and infinity. So absolute value, u should dv dv, so dv dv actually we have a v positive u and minus u, so that's why minus u to positive u. And another one v, so du, so here absolute value of v to infinity. As for the result, I think you can check how to reach the result. I just let you know how to set the range. Alright, so this is the direct application of the formula. And next one we want to let you know auxiliary variable. What it means if we can see the function defined in the previous supplement 2. And if we want to pass on the current result, supplement 3. So we should define two variables. So we can define this variable serving as the auxiliary variable, or this variable serving as the auxiliary variable. So that's why we can have an example. This example, oh, this is a function previously we expect. And right now, this is an auxiliary variable. All right. And based on the auxiliary variable, we need to find x and y. And so that the partial one should be, oh sorry, this is y first and then x. And partial 1 minus 1 and 0 and 1. So finally it's 1. This is a Jacobian. So it's 1 Jacobian ZW. And actually the inverse should be 1 again. So that's why we have a 1 for the this one. And so that Z and W, 1 Jacobian multiply the corresponding 1. And x actually is equal to Z minus W and W. And right now we have the margin, sorry, the joint. But right now we want to find Z, so it's marginal 1. Marginal 1 in perform integral. And we have a W. And W actually normally it should be negative infinity to positive infinity. So that we have the result based on the formula. And this way to derive the result, this result agree with the result in the previous supplement. You can check it. And for next one, actually I skip it, so serving as a reference, but I skip it. And finally, we have this example talking about the discrete random variable. So that we need to have the PMF. And this time we assume independent, identically distributed geometric random variable. What kind of geometry? This kind of geometry. P multiply Q to raised power to K. And K from 0, 1, 2 to the others. And we have two subproblems, A and B. And A want to show independent. And likewise independent. So independent, how to show independent? We need to have the joint PDF and marginal PDF. And the product form of the marginal PDF equal to the joint PDF. And then we can have the way to prove independent random variable for the current newly defined two variables. Well, so this is a goal of the problem. So let's check how to do it. So this is the first one. Oh, minimum equal to Z, and xy equal to x minus y equal to W. So we should have this Z minimum. So we can have this condition and this condition will equal to y will equal to x. So we want to have the joint PMF, and joint PMF actually we can have the universal set, but condition 1 and condition 2. And once condition 1, so we have a y, and condition 2, so we have x, y, and x. Condition 1, condition 2. And based on the previous one, even we have the condition. So we have the product form. Alright, condition here. And condition here. Alright. And the polyphone again. So we have the result. You can check it. And because of the condition, so finally, with the joint one, negative n and positive n, so we can have an absolute value, and so that only m, and we have all values. And this one, they are joint PMF, and we need to find the marginal PMF. So how to find it? Here we have a z, so we should have summation with respect to n. Summation. And you can have this, and finally we can have the result. I skip the details, you can check it. And likewise, you can find marginal PMF for W. Likewise, we have the result, and we notice, oh, okay, using the previous derived joint PMF and the marginal PMF, they can find the polyphone, so we can have the independence of the two random variables Z and W. And follow the similar way for subproblem B, but this time we have a minima and maxima minus minima. So we have a Z and R. And follow the similar idea to have the partition, to have the condition. So we can find joint. And we can find the corresponding marginal PMF. And likewise, we can have the polyphone to have the independence of random variables Z and W. For the second part, I go through quickly, but actually you can refer to the derivation, and so they can know why. Okay, so that's all. This is the supplement 3, and see you next time. Bye bye.